Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today we're going to finish a unit by talking about optimization problems. And I think you'll pretty quickly figure out what optimization means once we get into a problem or two and you realize what they're asking you to do. So let's look at this introduction problem. I would stop you before you go any further, and if you can, secure a regular 8.5 by 11 sheet of paper. It doesn't matter whether it's white or a different color. Get a pair of scissors and some tape because you're going to be building something for this problem. Now, your job is to take that sheet of paper and cut squares out of each corner. When you've cut squares out of each corner, you're going to be able to fold up the two sides to create a box, and then you can measure the different dimensions. You have to cut squares, otherwise the sides are not going to match up, and you need them to if you're going to create a box. So again, it's a kind of on you. You're just trying to figure out, okay, how big of a square should I cut out from the corners so that when I fold the box up, I'm going to get the most volume possible. So when you've created that box, when you've taped it together, again, no lid on the box, no top, you are going to write down the dimensions. So you actually may need a ruler if you have one to measure the length, width, and height. And you're going to write down the volume. So multiplying the length, width, and height together. And then we're going to actually figure out what the maximum volume of the box could be had we made our cuts in the exact right spots. So go ahead, try to build that box, and then we'll see how close you were to the perfect box. All right, so hopefully you have a box in front of you. Hopefully you've measured the length, width, height, and found the volume. And maybe you think this box is pretty close to the maximum volume, or maybe you think it's pretty far off because you weren't really sure what to do. So let's throw calculus at this problem. And we can think of what keyword from calculus is relevant when we are trying to find the largest possible something, or in this case, the largest possible box. You could also think about what the highest point on a graph would be called. And this would be called a maximum. So we're trying to find the maximum volume that we could create with a box. And optimization problems are going to be problems where you need to find the max or the minimum value of a function. And there's plenty of areas in the real world where people or companies are trying to minimize or maximize something, right? Most companies are trying to maximize profit while trying to minimize the costs themselves. If you want to think a lot about a hands-on example, company, I don't know, we could say a company who makes soup cans, right? They may want to make the largest possible volume in a can using the least amount of aluminum or steel or whatever they're making. I guess they're not making their soup cans out of steel, but they might want to fit the most amount of soup into a can using the least amount of aluminum. So definitely applicable to the real world, these different types of optimization problems. So basically, we're going to be figuring out how to use derivatives to find the minimums or maximums. And we're going to be applying these to real world scenarios. So before we move any further, think about how we use derivatives to find the minimum or maximum value of a function. And go ahead, write those steps down below. How do we use derivatives to find the minimum or maximum value of a function? All right, so I just put the steps up here. Obviously, first we're going to find the critical points where f prime is either undefined or equal to 0. And then we have two options, right? To look for a maximum or a relative maximum, we look for where f prime goes from positive to negative. For a relative minimum value, we look where f prime goes from negative to positive. And if we are looking at a function on a closed interval, well, if we're trying to find the absolute maximum, then we would also have to check those endpoints. Same thing with an absolute minimum, right? If the function's on an open interval, we are only going to be looking at the relative maximums or minimums. But if we're looking at a function defined on a closed interval, then we also have to check the endpoints. And that just goes back to the EVT, or the extreme value theorem. So sometimes in these problems, the domain is going to be an open interval. In that case, we only have to check the relative maximums or minimums. In some cases, it could be a closed interval. And in that case, we would check the endpoints as well. It's also possible that maybe on one end of the interval, it's a closed interval, and on the other end, it's an open interval. But we'll dive more into that when we see specific problems. We are going to start off by, again, applying calculus to the problem you guys worked out by hand with the paper. So again, we have an 8.5 by 11 inch piece of paper, and can we figure out what the largest possible volume would be if we made the perfect cut? So the first thing we're going to do is come up with an equation for the volume. Volume of a rectangular prism, we'd have V is equal to length times the width times the height. Now, we don't want an equation in 3 variables. We want to make this equation or rewrite it in terms of just one variable. So let me sketch a quick diagram of what our box or paper first, and then what the box looks like, and then that may help us be able to rewrite this equation in terms of just a single variable rather than 3. Okay, so on the top I have my piece of paper, my 8.5 11 by piece of paper. So 8.5 by 11. However, to form this box, I'm going to be cutting these squares out of the corner so I can fold it up, and then we'll get something like what I drew down here. So I need to pick a value for the length of the sides of these squares. And they are going to be squares, and they're all going to be the same square. So we would just have x and x represent the side lengths there. Which means that we actually need to measure this distance right here, because that's going to be the new width of our box when I fold it up, right? Because I'm going to be cutting out those corner pieces. So this width right here would be 8.5 minus 2x, right? Because I'm subtracting off an x from either side, right? The entire thing was 8.5. If I subtract off x's from either side, we'll be subtracting 2x. Same idea for the length. Oops. When I cut off those end pieces, this becomes my new length. So 11 minus 2x. So if I go down to my 3-dimensional image, I now know what my length is. My length is 11 minus 2x. I know that my width is 8.5 minus 2x. And my height, right, well, that's just going to be x. So now I have my 3 dimensions written all in terms of x, and I can rewrite my volume equation just in terms of x. So my length, 11 minus 2x, my width, 8.5 minus 2x, and my height ends up just being x. And if you go through and multiply these 3 factors together, I end up getting volume is equal to 4x cubed minus 39x squared plus 93.5x. And I don't think we need to go through all those steps in the video. You could just go through the distributing on your own, but that's what we should end up with. Now we're trying to figure out what's the maximum volume that I could create here based on the x value that I choose to cut out for my square. So if I'm trying to find the maximum value of a function, right, we talked about this, I need to figure out where the derivative goes from positive to negative, which means I first need to find my derivative. So I get v prime is equal to 12x squared minus 78x plus 93.5. And again, I'm going to set that equal to 0 to find my critical points. We don't have to check to see where this is undefined, because it's never going to be undefined. It's a polynomial. So we know it's not going to be undefined. We only need to check to see where the derivative equals 0. And then we can look at those points, look at those x values, and see whether the function goes from positive to negative at them. This is certainly not one you're going to try to factor. This would be a calculator problem. So you can just substitute this into y1 and see where the graph crosses the x-axis. And it turns out that there are two spots where this function crosses the x-axis. We get x is approximately equal to 1.5854, and x is approximately equal to 4.9146. I did end up rounding to the nearest 10,000th. You may say, well, why aren't you just rounding to 3 decimal places? Well, it's because these values aren't going to be our final answer. If they were, I would just round to 3 decimal places or truncate to 3. But if I need to use a value in the middle of my problem, I want to round to more than 3 decimal places because it's going to make my final answer, which needs to be 3 decimal places, be more accurate. So we have these two values where the derivative is equal to 0. Now we need to see which one of these is where the function, or the derivative rather, goes from positive to negative. And you can just use your calculator to do that, right? So let me just erase some of this for us. Let me just sketch a quick graph of what the derivative looks like so that we're all on the same page. So our derivative came down like this and then went back up. That's what the parabola looked like. Something like that. So we can clearly see that it's going to be at this 0, where x is approximately equal to 1.5854, that the derivative goes from positive to negative. So we are going to be using this x value to find those dimensions that create the largest volume. Now, something to note, something that may be interesting, is that this value right here actually wouldn't even be a possible value, right? If we cut 4.9 inches, right, out of each of these corners, well, if the entire side here is 8.5, there's no way that each of those cuts could be 4.9, right? Because that both of those combined would be more than 8.5. So even if our function had gone from positive to negative at that x value, we would have to be aware that that's not actually a possible solution anyway, right? The most we could cut, the most we could make our x cut would be 4.25, right? Because that would be half of 8.5. So, well, actually something less than 4.25, right? Because we need to have a width. So just pay attention to what the x values are. In some cases, they may not even be a possible solution because they may not fall in the domain of what our values could be, right? If we think about the domain for these x values, well, we have to cut out something more than 0, right? X has to be more than 0, but it has to be less than 4.25, right? Because again, if these were more, or if these were 4.25 or more inches, well, then we would have no width at all, and that wouldn't work, right? So even though it wouldn't have screwed you up in this case because that value wasn't a maximum anyway, it's good to think about, why that value could or couldn't have worked, even if it was a maximum. Okay, I know that was a little tangent here, but something good to think about. So we know the x value that we need to use, and now we just need to find those actual dimensions, right? It just says find the dimensions. It doesn't say find the actual volume. It just says find the dimensions of the largest possible open box. So we know that our length was equal to 11 minus 2x. So that means our length is approximately equal to 11 minus 2 times 1.5854. And that's going to give me an approximate length of 7.829 inches. We do the same thing for our width. I'm going to skip the first step. Our width is approximately equal to 8.5 minus 2 times 1.5854, which means my width is approximately equal to 5.329 inches. And my height is just the value of x. So height is approximately equal to 1.585 inches. Again, our final dimensions we can round to 3 decimal places. So this is the process of optimizing something, right? We optimize the volume here to figure out what the maximum volume of this box could be. Okay, let's see if we want to do any more problems, or we may just make a part 2 here actually. We will go over these steps, I think, and then we'll save these other problems for a part 2. So just some steps that you can think through when you're solving an optimization problem. Make sure you identify all the given quantities and the quantity that needs to be minimized or maximized. Right? So in our previous problem, the volume was what needed to be minimized or maximized, and then we had to identify the length, the width, and the height. We made a sketch of the problem, because it was a problem that was definitely conducive to a sketch. It was a geometry sort of problem. We wrote our primary equation that needed to be minimized or maximized. That was the volume. And then we had to go through that process of reducing the primary equation to one that has a single variable, right? So we had to rewrite the length, width, and height all in terms of x so that we could then take the derivative later with just respect to x. We did take a look at what the domain of our volume equation could have been, right? We said that our x had to be on a domain of 0 to 4.25. It wasn't necessarily prudent that we did that for that specific problem because our solution ended up being on the domain anyway, or the only possible solution ended up being on the domain. So we wouldn't have messed up if we had just skipped that domain part. But sometimes solutions or possible solutions may not be in that domain, and we have to check it against it. And then we determine the desired maximum volume using our derivative techniques. So again, just things to think about when you're doing these optimization problems. Any problem that's asking you to find a minimum or a maximum, those are going to be a type of optimization problem. Okay, we'll come back for part 2 where we work through some other types of examples. As always, enjoy the rest of your day, and I look forward to seeing you next time.